Over the last few lectures, we have been taking a look at some of the topics in quantum mechanics that you had already seen in previous courses, but in perhaps somewhat more detailed a manner. This is the last lecture in that series, and here we are going to take a look at what is often considered the pinnacle of an elementary quantum mechanics course, the hydrogen atom. We are going to actually talk about the mathematics involved here in perhaps a bit less detail than we had already done for the previous topics. This may come as a bit of a surprise because usually the hydrogen atom is treated in some great detail in most courses. However, what I want to point out is that the mathematics that we need to handle this particular problem has already been discussed in various other contexts in the few lectures that I have given so far. And what we will do today is basically use those results to try to quickly arrive at the result for the hydrogen atom. Let me point out one thing. Over the last 4 or 5 lectures, we have been talking about a single point particle moving in a central potential. The hydrogen atom, of course, is not one point particle but two. There's an electron and there's a nucleus. And it's a two-body problem that we really have to deal with. So at the very beginning, we will have to show how this two-body problem reduces to an equivalent one-body problem, and then show that this equivalent one-body problem, at least one part of it, can be handled with the methods that we have been describing so far. In that context, all the mathematics that we have talked about so far, like the angular equations, the spherical harmonics, etc., are going to carry through as previously. The new thing will be the radial equation you will get for the relative part of the problem. You will soon see what I mean by that. And this relative part of the problem is what we are going to take a look at by borrowing some of the mathematical results that we have already established in the last few lectures, especially in the last lecture on the spherical harmonic oscillator, because there we had met a class of differential equations called the confluent hypergeometric equation and its solutions, the confluent hypergeometric series. In fact, we had met a particular version of confluent hypergeometric series called the Laguerre polynomials, and we are going to need them again in the solution to the hydrogen atom problem. Let us start by taking a look at how to reduce the quantum mechanical two-body problem to effective one-body problems. The procedure, as you will soon see, is very similar to what is done in classical mechanics. There you talk about center of mass and relative coordinates. We do exactly the same thing here. The mathematics is slightly different, but the essential results are all the same. As you all know, the hydrogen atom consists of an electron in the vicinity of a positively charged nucleus. And we are going to deal with hydrogen atom-like problems, which means you have a single electron, but perhaps multiply charged nucleus. So, in addition to the hydrogen atom proper, this also covers helium plus, lithium double plus, etc. Now, the Hamiltonian which describes the hydrogen atom is given by this expression here. You have a minus h cross square by twice m1 Laplacian 1, the kinetic energy term corresponding to the first particle, in this case the nucleus, and minus h cross square by twice m2 Laplacian 2. This is the second particle's kinetic energy contribution. That's the electron here. In addition to these two terms, you have the additional potential energy, which, because the interaction is attractive, is negative compared to its value at infinity. So it's given by this very familiar expression, minus Z E square by 4 pi epsilon 0 mod R2 minus R1. Here E is the magnitude of the electron charge, plus ZE is the charge of the nucleus, Z being the atomic number, and minus E is the charge of the electron, which gives rise to this particular potential energy term. And as you all know, Laplacian 1 and Laplacian 2 are basically the Laplacian operators corresponding to the coordinates of particle 1 and particle 2. Now, just as we do in classical mechanics, we will be able to actually simplify this problem a lot by going over to different coordinates. In particular, the same set of coordinates that we use in the effective theory for the same system in classical mechanics. By the way, you don't use it only for the hydrogen atom problem, you use it for any two particles interacting among themselves. And classical mechanics tells us that the center of mass of this two particle system, which is interacting only among each other, is going to move freely, and the interesting dynamics will only be in the relative coordinate. Taking a cue from that, we do exactly the same thing here. We go over to center of mass coordinates written capital R here. Capital R, of course, is a vector. M1 R1 plus M2 R2 by M1 plus M2. And relative coordinates small r, which is R2 minus R1. In our problem, small r is really the position vector of the electron with respect to the nucleus. Of course, we can rewrite the equations in such a way that small r1 and small r2, the position vectors of particle 1 and particle 2 in the original coordinate system, can also be rewritten in terms of capital R and small r, which of course goes to show that the two coordinate systems are equivalent descriptions of the same situation. You can use either one or the other. However, using center of mass and relative coordinates will simplify the problem a lot, as you will soon see. And that, of course, is our motivation for doing that. What we need to do right now is be able to rewrite the Laplacians, which are with respect to the coordinates of particle 1 and particle 2, in terms of other Laplacians, which are in terms of the components of the center of mass vector and the relative vector. For this, what we need to do is be able to write the components capital X, capital Y, capital Z of the center of mass vector and small x, small y, small z of the relative vector in terms of the components of R1 and R2. And I'm going to just show you how this goes for capital X and small x, that is the x components of R vector and small r vector. The treatment for capital Y, capital Z, etc. are very similar, and there's no point in repeating the calculation all over again. You can easily see the pattern which is going to emerge. So capital X, of course, is given by small m1 small x1 plus small m2 small x2 divided by m1 plus m2, and small x is obviously x2 minus x1. So far, this is very straightforward. What we need to do is change derivatives, del x1, del x2 and so on, in terms of this capital X and small x. For that, we use a chain rule for derivatives. Del x1 is given by del capital X, del capital X, del x1, plus del small x, del small x, del x1. Of course, when I say del capital X, I mean at small x, small y, small z, etc. constant. When I say del x1 here, I mean small x2, small y2, small y1, etc. These things constant. Now, it's pretty easy to calculate this result. It's trivial nearly. The derivatives involved here can be immediately read off from the line above, and it turns out that del small x1 turns out to be m1 by m1 plus m2 del capital X minus del small x. And a very, very similar calculation will be able to give you del small x2. And del x small x2 will turn out to be almost identical to this expression, except that you get a plus sign here instead of a minus sign. That's obvious. You had a small x2 minus small x1 for small x. So one derivative is negative, which is showing up here. The other derivative, of course, is plus 1. And here, the coefficient in front of del capital X is m2 by m1 plus m2. So that's what you have for the first derivatives. What we need is, of course, the second derivative, del 2 del x1 square, del 2 del x2 square, and so on. And that's straightforward. You can form del 2 del x1 square by essentially squaring this operator. And here, because del capital X and del small x commute with each other, the calculation proceeds exactly like what ordinary algebra would have told you. You get the a squared term, b squared term, and a minus 2ab term. So, m1 by m1 plus m2 whole square, del 2 del x2, plus del square del small x square, minus twice m1 by m1 plus m2 times this mixed partial derivative. And an exactly similar expression occurs for del 2 del x2, where essentially you have a plus sign instead of minus 1 and an m2 m1 switch. Now what we really need, of course, is Laplacian 1 by m1 plus Laplacian 2 by m2. So if you just look at the x derivatives, what you need is this combination. 1 by m1 del 2 del x1 square plus 1 by m2 del 2 del x2 square. And it's very easy to see that if you divide the first expression here by m1 and the second by m2 and add, the mixed partial derivative term is going to cancel. This one will contribute m1 by m1 plus m2 whole square. This one will contribute m2 by m1 plus m2 whole square. When you add them up, you just get a single 1 by m1 plus m2. And del 2 del small x2 square will have a 1 by m1 plus 1 by m2 combination in front, which should be a very familiar quantity from your studies in classical mechanics. So basically, if you repeat this for del capital Y, del capital Z and so on, you will find that the Laplacian 1 by m1 plus Laplacian 2 by m2 simply turns out to be 1 by m1 plus m2 Laplacian with respect to capital R plus 1 by m1 plus 1 by m2 Laplacian with respect to small r. And these quantities are very familiar. m1 plus m2 is just nothing but the total mass of the system, capital M. And this quantity 1 by m1 plus 1 by m2 is a reciprocal of what is known as the reduced mass of the system. So you can rewrite this as 1 by small mu, and mu, of course, is m1 m2 by m1 plus m2. A very, very familiar expression that you have seen over and over again whenever you have dealt with two-body systems in classical mechanics. Here we are seeing the same quantity emerge as an important entity in quantum mechanics as well. So the next step in our analysis is simply to rewrite the Hamiltonian of the hydrogen atom, basically the two-body system that we are talking about, this one, in terms of capital R and small r. Of course, one obvious thing is the potential energy depends only on the magnitude of small r vector, which is the small r quantity here. So what we have is the kinetic energy pieces become the sum of these two pieces. Small m1, small m2, of course, gets replaced by capital M and mu, and the potential energy term only has small r in it. So this problem essentially breaks up into two problems. One which involves the center of mass coordinates and center of mass coordinates only, where the Hamiltonian piece only has a kinetic energy term, which means it's obviously a free particle. And the rest of the Hamiltonian, the second part, is simply the Hamiltonian for a single point particle whose coordinates is given by small r vector, moving in a central potential given by minus z square by 4 pi epsilon 0 small r. What I'm going to do next is rather trivial, but it's important to explicitly realize what we are doing. The energy eigenfunctions that we want to calculate for the system are actually eigenfunctions of the full Hamiltonian H, and they are functions of capital R and small r. The energy eigenvalue, of course, is what we are calling E total here. The thing written in black, of course, is the Schrödinger equation for the two-body system. Now, because of the simple form of the Hamiltonian that we have, a Hamiltonian which involves only the center of mass coordinates and another piece which involves only the relative coordinates, it's obvious that we should try this particular ansatz for separation. We can separate the capital Chi, which is a function of capital R vector and small r vector. Remember, this actually used to be a function of small r1 and small r2, but we have relabeled the coordinates here. We can write this as Chi Cm capital R times Chi of small r. Two wave functions, one which describes the center of mass coordinate system, the other which describes the relative coordinates. It is rather trivial to see that this is going to cause the Schrödinger equation for the composite system to split into two equations. The separation in this case is rather trivial, and what you are going to end up is with sum of two terms like this, one which involves only the center of mass coordinates and another which involves only the relative coordinates. Of course, what this is going to tell us is that both pieces are constants, and these two constants add up to the total energy E total. Then, of course, hence energies in their own right, and we label them ECM for the center of mass energy and E for the relative energy respectively. We are going to call the relative energy E because that is the one which we are going to focus on primarily in this lecture. But before we start talking entirely about this equation here, let me just point out that you end up with two Schrödinger equations effectively. The first one, rather obviously, is the Schrodinger equation for a free particle with mass capital M and energy ECM. So the center of mass essentially behaves like a free particle as it did in classical mechanics. We will not talk any more about this in this lecture simply because we have already learned earlier how to handle free particles. However, let me point out that the total energy of the hydrogen atom, of course, is the sum total of the energy E that we usually talk about as the energy levels of the hydrogen atom and the kinetic energy term from the center of mass, which comes from this equation. Of course, the kinetic energy term for the center of mass, being the kinetic energy for a free particle, is not quantized. You have a continuum of energies for ECM. On top of that, you will get discrete quantized levels of energy coming from this equation, which will tell us that E will turn out to be quantized, at least the negative values of E, the bound states, bound energies will turn out to be quantized. Now, this is what the equation is going to look like, which, let me point out, is the equation of a single point particle of mass mu moving in a potential minus z square by 4 pi epsilon 0 r. So, what we have managed to do is we have managed to reduce the two-body problem into two one-body problems. The first one, a free particle which describes the center of mass motion, and the second one, an effective particle of mass mu in a potential of minus z square by 4 pi epsilon 0 r, a 1 by r potential. This is essentially the potential of a single point particle which is moving in the field due to an immobile, infinitely massive particle at the origin. This particular problem is called the Kepler problem, after the famous astronomer scientist who had laid the groundwork for Newton's discovery of the inverse square force and the 1 by r potential as a consequence. And since this is a central potential problem, all that we had studied about earlier about central potential supply, the wave function, which is a function of small r, theta and phi, can be split up in this particular form, where the angular part is given by the spherical harmonics y, l, ml, theta, phi, and the radial part is described by a radial function which depends on E, the energy, of course, and L, and is a function of small r alone. In what follows, I am going to omit the E and L labels from the equation simply because we know that they are always there and we don't really want to clutter up our equations too much at this stage. The radial equation that we have already studied several times is given by d2 capital R dr2 plus 2 by r d capital R dr plus 2 mu by h cross square times energy minus the potential energy. But in this case, instead of subtracting just the actual potential energy, you have to also put in an additional piece, which is h cross square L into L plus 1 by 2 mu r square, the so-called centrifugal potential barrier term, which essentially is a consequence of the separation that we had to do in order to arrive at this equation in the first place. Of course, in classical mechanics, as we have already pointed out, you do have the centrifugal potential barrier term in the effective potential, so that sort of mimics exactly what we had done earlier. Given an equation like this, the first step would of course be trying to simplify the equation's appearance by going over to dimensionless variables. We have already described this in great detail in earlier lectures, in fact from the very first preliminary lecture that we had. So I would have liked to omit this particular detailed discussion here, but still I am doing this to point out one very important thing. What we do here, of course, is replace r by this variable rho with a proportionally constant alpha to be determined in front. And if you put that in, it's rather straightforward that the second derivative will become 1 by alpha square d rho 2 and so on. Here you get an alpha square 1 from r, 1 from the ddr. That's sort of straightforward. After you multiply through by alpha square, you end up with this expression. What I really wanted to point out here is that now you have a choice of either simplifying this expression or simplifying this expression. Now, different authors actually use both approaches, and given the much more formidable looking form here, I'm pretty sure most of you would love to have simplified this one. But I would suggest that the proper thing to do would be to try to get this as simple as possible, and let me stress the reason why. Notice that this equation is one which has singularities, and our standard dictum has always been know your enemy, that is, know the singularities of the equation. This equation has a singularity at rho equal to 0, which is rather obvious. You can see it right in front of your eyes here because of the 1 by rho and 1 by rho squared terms. Let me also point out that this is a regular singularity, so although it's a singular point, it's not that bad a problem. But let me point out that it is handling the singularity at rho equal to infinity which is going to take great care. So it would be rather prudent of us to try to handle things in such a way that the equation becomes simple for rho going to infinity. Now, of course, when rho goes to infinity, the 1 by rho and 1 by rho squared terms drop out, and the constant term 2 mu e by h cross square alpha square is the one which survives. So that is the one we are going to simplify here. Note that the difference between this case and the harmonic oscillator case that we tackled in our first lecture is that in one case we are trying to simplify the constant term, in the other we try to simplify the term with x square in it. But the motivation is the same in both cases. The dominant term at large x or large rho, as in this case, is the one we have to be careful about because that's where the irregular singularity is. And that is why we choose to simplify this particular term in the expression at the expense of keeping the other term unsimplified. Given this, you might have thought that the obvious thing to do would be to choose 2 mu e by h cross square alpha square to be 1. But of course we can't do that because remember we are looking for the bound states of the system. And the bound states for a system where the potential energy vanishes at infinity as it does here have negative energies. The capital E's that we are looking for are all negative. So we would have perhaps written this better as minus 1. But instead of that, I choose to write this as minus 1/4. This is simply because of, convenience later rather than right now. But anyway, it's a constant, so it's pretty straightforward to handle. So this is the expression for alpha that you are really writing down. And then the entire stuff here, 2 mu by h cross square z square by 4 pi epsilon 0, the coefficient of 1 by rho, times alpha. If you put that all in together, along with the value of alpha, you get a constant which you are going to call capital K. So in this expression, of course, capital K is what depends on the energy, and showing that capital K can only take certain values to get a physically meaningful wave function would end up telling you that energy, capital E, can only take certain values. That is, energy E is quantized. Now with these changes, the equation ends up looking like this. So the d2r d rho 2 by 2 by rho dr d rho terms are there as always. This expression has become minus 1/4, and this one has been replaced by capital K by rho. Minus L into L plus 1 by rho squared is there as always. So following the dictum of know your enemy a bit better, we now first investigate what happens to the behavior when rho is very, very large. And of course, when rho is very large, the 2 by rho dr d rho k by rho L into L plus 1 by rho square, all these terms drop out. And the equation becomes d2r d rho 2, which is almost equal to rho by 4. That's the minus 1/4 here. And that is a very, very straightforward standard equation to solve, and we know its solution. The solution is e to the plus minus rho by 2. So the behavior of a solution to this equation when rho is very large has to be either e to the plus rho by 2 or e to the minus rho by 2. By the way, one reason why we chose 1/4 there is so that we can end up with a plus minus rho by 2 here. That will have two advantages. One is, after we try to choose e to the minus rho by 2 as one possible behavior, the multiplying function which we are going to choose can then either behave like a decent polynomial, and hence capital R will end up behaving like e to the minus rho by 2, or it can try to look like e to the rho, which will lead to capital R of rho to be e to the plus rho by 2. It's the e to the rho in the asymptotic behavior of this multiplying function, which is what we are aiming at, which is why we chose a minus 1/4 rather than a minus 1 there. Another important point is this capital R of rho is going to go into a wave function. So you're going to take the mod square of that in most calculations. So e to the minus rho by 2, which is present here, will become e to the minus rho. Of course, that will simplify some of the algebra a tiny bit. So that is the real motivation behind the 1/4. As you can see, it's really not that urgent a thing. So some authors put in a minus 1/4, some authors write it as minus 1. Some authors even, of course, go in for simplifying the other term, the one with z's and stuff. But that actually is not that great an idea. This one will make your final expressions a lot easier. Our other enemy, the other singularity of this equation, is sitting at small rho. In fact, it's sitting at rho equal to 0. And what we need to do is be sure of the behavior of capital R when rho becomes very small. Now, the differential equation that we have has a regular singular point at rho equal to 0, as you can see from this expression rather easily. The capital P term has a 1 by rho, first order pole. Capital Q term has 1 by rho square, a second order pole. This, remember, is the criterion that we had said would give you a regular singular point. And hence, you will expect no essential singularities here. So, one important feature here is that we will expect a Frobenius-like solution to the problem around rho equal to 0. So, you can write the solution in powers of rho, but powers which do not necessarily start at a constant. It starts at rho to the s. Now, notice that if we want to look at behavior only very close to rho equal to 0, it's just the s in the rho to the s that we really should worry about. Higher power terms will be dominated by rho to the s anyway. And how do we figure that out? Well, this expression, of course, gives you rho to the s minus 2. This one also gives you rho to the s minus 2. This gives you a higher ordered expression. This one gives you rho to the s minus 2, starting from rho to the s. So lowest power can come from this term, and this term. If you take the coefficients together, this will give you s into s minus 1. This will give you 2 times s from the derivative. And this, of course, gives you minus L into L plus 1. The 3 put together gives you this indicial equation. The equation which tells you the dominant behavior of R as rho becomes very small. And if you solve this quadratic equation, you get 2 possible roots. So capital R for very small rho has these 2 possible behaviors. Rho to the L is 1 root for S, and 1 by rho to the L plus 1 from the other root. Obviously, this is the one which is well behaved as rho goes to 0. This is the one which is going to diverge, and hence the one we don't want. So putting together our knowledge about the behavior of the function capital R when rho becomes very large and when rho becomes very small, we note that the behavior we would like at these 2 extremes would be like rho to the L in one end and e to the minus rho by 2 in the other end. But these, of course, are only asymptotic behaviors of the function. So in order to be able to manipulate the function and ensure that the asymptotic behaviors stay the way we want them to be, rather than go to the other divergent terms, we start by making this change of variables. R of rho is now written as rho to the L e to the minus rho by 2 times another function f of rho. And what we will do is we will try to solve for the function f of rho. Note that, as we have stressed before several times, making this change of variables does not ensure that the wave function capital R will turn out to be well behaved at the end of the day. Capital F still has a potential for diverging badly. In fact, it has a potential for diverging as e to the plus rho when rho goes to infinity, and 1 by rho to the 2L plus 1 when rho goes to 0. So that capital R at the end of the day ends up behaving badly like e to the plus rho by 2 or 1 by rho to the L plus 1. It is this possible danger that we want to avoid. And this is what we have to guard against in our entire calculation. Let me repeat once again what I had told you before, but it's an important enough point and it requires stressing. You could, of course, solve this equation directly by using the Frobenius method. Rho equal to 0 is a regular singular point, so Frobenius method would work. But if you tried that, this would give you rho to the power n minus 2. This would give you rho to the n minus 2. But these three terms will give you rho to the n, rho to the n minus 1, rho to the n minus 2 respectively. So we'll end up with a 3-term recursion relation. And when you are trying to deal with the potential divergence as rho goes to infinity, having a 3-term recursion relation, as we had pointed out before, is not a great idea. So as we will see, the substitution that we have done, bringing in rho to the L to the minus rho by 2 outside the factor f, will lead to an equation for capital F which will be easier to handle. Now we are not going to dwell too much on the algebra here, but what I do want to point out to you is that I find it easier to carry out the calculations if I take this rho to the L e to the minus rho by 2 term as an overall factor at each step of the way when I evaluate the derivatives d capital R d rho and d2r d rho 2. Of course, when you are actually calculating the first derivative, there is one term in which this is really the factor as it stands because you are differentiating the other term. However, there will be one more term where f will stay intact and you will have to differentiate this factor. Now, when you differentiate rho to the L, what you get is L by rho times rho to the L. So that's an overall L by rho factor beyond the rho to the L. On the other hand, when you differentiate to the minus rho by 2, you simply get an extra minus half. So basically, whenever you are differentiating a function which is multiplied by rho to the L to the minus rho by 2, you get the overall factor times the derivative of the function plus the function itself times L by rho minus half. So that is what we are going to use once again when I differentiate this function to get d2 capital R d rho 2. You have the overall factor rho to the L to the minus rho by 2. Then you differentiate this function, which obviously gives you d2f d rho 2. Then this one gives you L by rho minus half times df d rho. And you also have to differentiate the L by rho term here to get an extra minus L by rho square f. But that's only from the differentiation of this factor. I also have to get an extra L by rho minus half times this factor overall. So that's the extra piece. And after that, it takes a bit of algebra to gather the terms together. And if you do that, what you're going to end up with is this expression, rho to the L e to the minus rho by 2 times d2f d rho 2 plus 2L by rho minus 1 df d rho plus L square minus L by rho square. All I've done is actually gather the terms together properly, and minus L by rho plus 1/4 times f. Now this is only from the individual derivatives. When we put them all together and substitute in the original equation, this is what we are going to get. And if you do that and drop the factor rho to the L to the minus rho by 2, which is not 0 for any non-zero rho, cancel it out. You end up with these three terms. The term in blue is what is going to come from the d2r d rho 2 term, which is this bracket here. The two terms in green actually comes from the dr d rho term, and the term in orange, of course, is a term which came from just the r times minus 1/4 plus k by rho minus L into L plus 1 by rho square term. Now if you combine all of them together, some rather nice things happen. For example, if you look at the 1 by rho square term here, that has an L square plus L in the numerator. You have an L square minus L times 1 by rho square term here. You also have a 2L by rho square term here. So if you take all of them together, they simply cancel out. And so the dominant, the most troublesome term as rho goes to 0, the 1 by rho square term, that simply cancels out. That should not come as a surprise. We had already taken the rho to the L behavior out of capital R. So the resulting capital F has a possibility of behaving like rho to the 0, which is essentially what this dropping out of 1 by rho square term ensures. By clubbing together all the other terms appropriately, of course, these two together will give a df d rho term of 12 plus 2 by rho minus 1 and so on. And with some very simple algebra, you will end up with this equation for d2f d rho 2. And if you multiply through by rho to exhibit the differential equation structure here, what you end up with is this. Rho d2f d rho 2 plus a constant minus rho df d rho plus another constant k minus L minus 1 f equals 0. At this stage, you should get a feeling of deja vu, especially if you have listened carefully to the last lecture. In the last part of the last lecture, what we have talked about is a differential equation which has a regular singular point at 0 and another regular singular point at infinity. Of course, our equation has the same structure, but we were talking about a special differential equation of that kind, one with a very special form. This happened to be called the confluent hypergeometric equation, which in a standard form was written x d2 by dx2 plus c minus x t by dx minus a times y equal to 0. A and c are the two parameters describing this problem, and you can see right now that apart from the fact that x is called rho in our equation and y of course is called capital F, this equation is exactly of this form where c is 2l plus 2 and a is l plus 1 minus k. So let me remind you that in the last lecture, we discussed the properties of the solution of the confluent hypergeometric equation in some detail, and there we had pointed out that this would usually give rise to solutions which are infinite series, but we already anticipate that infinite series will give us problems, because we know that capital F has this potential for divergence as rho goes to infinity. Divergence like into the rho. In fact, I would urge you to check that if you tried solving this by using the standard power series method, which you of course can, not the power series method, but the Frobenius method really, because rho equal to 0 is still a singular point, and then check the ratio of the coefficients as the powers go to very high values, you will find that same ratio as you get in e to the plus rho. This is a calculation which is very similar to the ones we have done so far. So we are simply going to borrow those results for the purposes of the present lecture. We know that capital F can diverge as rho goes to infinity. In fact, will diverge as rho goes to infinity, unless we ensure that it is not an infinite series. And how do we manage to do that? We already have studied in the last lecture that the confluent hypergeometric equation gives you finite polynomial solutions only when a is a negative integer, or here k minus l minus 1 is a positive integer or 0. So let's call this small k. Small k can take values 0, 1 and 2, and capital K, which remember is related to the energy, takes the form small k plus l plus 1. So l already is an integer. What we can see here is capital K can take values which are l plus 1, l plus 2, l plus 3 and so on. And this is what we call the principal quantum number and label it by n. Let me remind you that capital K is related to the energy. So the fact that capital K can only take some positive integer values tells you that energy must be quantized. We will look into that soon, but before that let me just take a look at what the wave function is going to be. Remember that capital F is a part of the radial wave function, and this of course satisfies the confluent hypergeometric equation as we have been saying. And let me also remind you once again that this is the parameter c in the confluent hypergeometric equation, and this capital K minus L minus 1, which is also our small k, is actually minus a in the confluent hypergeometric equation. Also, let me remind you that from the last lecture we had learned that there are two independent solutions of the confluent hypergeometric equation, of which only one is regular at rho equal to 0, and that one is the confluent hypergeometric series 1f1 a comma c semicolon x, or in this case semicolon rho. So our capital F, the capital F function that we want, will have to be f rho 1f1 minus small k, this remember is our small a, 12 plus 2, that's our c, semicolon rho. And that of course can be related to the associated Laguerre polynomials, because let me again remind you, this is again from the last lecture, that if the quantity small a takes negative integer values, which in this case it does, it takes a value minus k, then what you end up with is a finite polynomial which is called the associated Laguerre polynomial. Please don't confuse this n here, which is the negative integer value which a takes, with the principal quantum number that we introduced a while ago. In fact, in our expression, small k plays the role of small n, and if you put that in, we see that capital F of rho will have to be proportional to this particular Laguerre polynomial. There are factors in the front, but after all that will be absorbed in the overall normalization anyway, and this is really capital L of 2l plus 1, small k is of course small n minus l minus 1. This n is the principal quantum number, not the n up here. So f of rho is basically an associated Laguerre polynomial with parameters n minus l minus 1 and 2l plus 1 of the variable rho. And when we plug this back into the expression for the radial wave function, we end up with this expression for r n comma l rho. Remember, in our original designation, r was parameterized by energy and l. Since small n is a stand-in for the energy, I am labeling it the standard way in which instead of e we are using small n. Capital R of small n comma l of rho is given by rho to the l e to the minus rho by 2, l small n minus l minus 1 to l plus 1 rho, which is the Laguerre polynomial, associated Laguerre polynomial. And there's an overall normalization factor which you can derive from the basic properties of the Laguerre polynomials. We have not gone into the depth of mathematical properties of the Laguerre polynomial for two reasons. One of them is we have already spent some time in studying the mathematical properties of other polynomials, and I don't really want this to become a mathematical physics course. However, we will study some of these derivations in the assignments, and as you might have guessed, we can actually derive all of these normalization conditions, etc., starting from orthogonality relationships between Laguerre polynomials, which in turn we will derive from their generating functions. Let us now turn to the question of energy quantization. Precisely what form does the quantized values of the energy levels for the bound states of the hydrogen atom take? Let me remind you of the relationships that we have started with. Alpha, the dimensional constant which essentially made R dimensionless, was given by root over h cross square by 8 mu minus E, and this was the relationship for capital K. Remember, capital K has now been shown to lead to meaningful wave functions only when capital K is a positive integer n. So putting that in, but you can easily show that energy E from this expression is simply minus z square by n square times E square by 4 pi epsilon 0 whole square times mu by 2h cross square. This particular combination, E square by 4 pi epsilon 0, is what will appear everywhere. So I have decided to club them together. And this turns out to be minus z square by n square times this quantity, which is called the ionization energy EI of the hydrogen atom. Why is this the ionization energy? Simply because the lowest possible energy, the energy of the ground state of the hydrogen atom, is obtained when the denominator here is the smallest. Remember, there's a minus sign in front. So smallest denominator means most negative energy. So the ground state energy of the hydrogen atom, where Z is 1, is actually given by minus EI. So plus EI is the extra amount of energy you have to give to an electron in the ground state of a hydrogen atom in order that it ends up with a total energy of at least 0, so that it can be free from the atom itself. Let me point out that I have labeled the energy with two parameters N and L, and in general, in a central potential, as we had discussed before, the energy would depend on L, but in this case, as you can see, the energy is independent of L. It depends only on one quantum number, small n. This happens to be a result of what used to be called accidental degeneracy. Why accidental? Well, the fact that the energy levels don't depend on ml is something which follows from rotational symmetry. And it is a general consequence of the theory of symmetries in quantum mechanics that if you have a symmetry, that leads to degeneracies. So the ml degeneracy, the fact that the energy does not depend on ml, is something can easily explained by the geometry of the problem, by the fact that the problem has a spherical symmetry. On the other hand, spherically symmetrical potentials do not lead to L degeneracy. This degeneracy which you see in this particular problem, this is not something which happens for an arbitrary central potential. So this has nothing to do with the spherical symmetry of a central potential which all central potentials have. It has something very specific to do with this 1 by r form of the potential which the Kepler problem uses. There does happen to be a symmetry underlying this particular degeneracy, and this symmetry is connected deeply with the particular form of the potential energy, that is this 1 by r form for the potential energy. Now this is an example of what is called a dynamical symmetry as opposed to a geometrical symmetry which we are more familiar with. Now there is a hint of this symmetry even in classical mechanics. As you all know, in the standard theory of central potentials in classical mechanics, there are two obvious conserved quantities. One is the energy and the other is the angular momentum. And the conservation of angular momentum in such systems is directly related to the spherical symmetry of the potential. However, for the specific case of the 1 by r potential, there is an extra conserved quantity in classical mechanics. It's called the Laplace-Runge-Lenz vector. And in fact, it is this Laplace-Runge-Lenz vector which is directly related to the dynamical symmetry which the hydrogen atom problem, or more precisely the Kepler atom, possesses, as a consequence of which you end up with this extra degeneracy. So it's really not an accidental degeneracy, but the name has stuck, and so that's the name that we are going to use. It is of course also interesting to rewrite the other quantity up here, that is the dimensional constant alpha, in terms of more familiar constants. So this is what it turns out to be. Alpha turns out to be n by 2z h cross square by mu times e square by 4 pi epsilon 0, and this combination h cross square by mu e square by 4 pi epsilon 0 is called a mu, the first Bohr radius of the reduced problem in the hydrogen atom. This is related to A0, the first Bohr radius, which we are more familiar with. A0 is the same expression with m sitting here, the mass of the electron, rather than the reduced mass. So A mu, of course, is m by mu times A0. And A0 can be written in many other different ways. One very useful way is this. A0 is h cross by mc divided by alpha fs. Alpha fs here stands for the fine structure constant. You must have realized that my choice of the name alpha for this dimensional parameter is rather unfortunate, because we are used to using alpha for the fine structure constant. Because I've already committed to using alpha for this particular parameter here, I'm going to call the fine structure constant alpha fs, at least for the purposes of this lecture. Alpha fs, as this formula tells you, essentially is the ratio between h cross by mc, which is the Compton wavelength of the electron, and A0 is first Bohr radius. So basically this is telling you that the Compton wavelength of the electron is roughly 1/137th of the first Bohr radius, which remember is about half an angstrom. By the way, the fine structure constant is also the ratio between the velocity of an electron in the semi-classical Bohr orbit, first Bohr orbit around the nucleus, divided by the speed of light. So this tells me that relativity will play a very important role in the theory of heavy atoms, where the electron would have to travel much faster in order to beat the attraction of the higher charged nucleus. Relativistic effects actually are quite important in atomic physics. Just as a matter of curiosity, let me say this out loud right now, that the bright yellow color which gold has is essentially a relativistic effect. Without the relativistic correction, the color of gold would have been dull brown. It is also possible to rewrite the ionization energy of the hydrogen atom in terms of these same parameters. It turns out to be h cross square by twice mu mu square and can be rewritten in this form, mu c square by 2 times the fine structure constant squared. So notice that the fine structure constant square essentially tells you how big the ionization energy is compared to the rest energy of the electron. The rest energy of the electron, of course, is mc square rather than mu c square, but the two are very close to each other. So this essentially tells you once again that the amount of energy you would need to ionize an electron is roughly 1/20,000 of its rest energy. Let me wrap up this lecture by writing down the full form of the energy eigenfunction for the bound states of an hydrogen atom, psi, n, l, ml. So these are the three quantum numbers, n, l, and ml, which describes a particular energy eigenfunction, the function of r, theta, and phi. And if you just take a look at it, it's not really something new. You already knew all these factors separately. You have the spherical harmonic y, l, ml, theta, phi. You have the Laguerre polynomial parameterized by n minus l minus 1 and 2l plus 1. This twice zr by n mu is simply r by alpha, which is my rho. And this is rho to the l sitting here. Here you have e to the minus rho by 2. This was a normalization constant you saw a while ago when we were talking about normalizing r of rho. This extra factor of 2z by n mu to the power 3 by 2 is actually what allows you to normalize the wave function in terms of dr. That is, the integral psi mod square dr has to be 1 rather than the integral of psi mod square d rho. That gives you this extra factor of 2z by n mu to the power 3 by 2. So we have come to the end of our discussion of the energy eigenfunctions of the hydrogen atom, except for one very important point which I must emphasize at this stage. The energy eigenvalues that we have found out and the wave function that I have written down for you right now all correspond to bound energy eigenstates. In addition to these bound states, the hydrogen atom has lots of so-called free states or unbounded states. States for which the wave function extends all the way up to infinity. And these are states with positive energy. It turns out that the positive energy states actually form a continuum in the sense that the energies which such states can take are not discrete. Such states can have any positive energy whatsoever. Now these states are extremely important in chemistry because you want to talk about a situation where the electron essentially leaves an atom, goes somewhere else, or in the theory of scattering. We will meet these states and some of their properties later on when we discuss such issues. For the time being, let this be all that we will say about the hydrogen atom right now. We will have a lot more to say about some of these other issues in the lectures to come.